For the first time in 50 years, 4 humans are about to leave Earth's protection. They are not just going to the moon, they are riding a controlled explosion into a radiation death zone, and NASA's backup plan is literally physics and luck. This is not a landing mission. It is a 10-day survival test where one failure means there is no rescue mission. Once Orion leaves Earth's orbit, there is no backup rocket waiting to chase it down. The crew's safety net is a path carved by physics itself, a figure-8 loop around the moon that brings them home even if every engine falls silent. This is the free return trajectory, the ultimate cosmic insurance policy. After the massive push from the Space Launch System, Orion's course is set so precisely that if all propulsion systems go dead right after the translunar injection, gravity alone will haul the capsule back to Earth. No fuel, no engine burns, just the relentless pull of 2 worlds shaping a curve through space. Fine-tuning along the way is possible. Orion's reaction control thrusters, each smaller than a car's engine, can nudge the trajectory by a few meters per second if needed. But these corrections are minor, using only a sliver of the available change in velocity. If the main engine fails, the crew does not need a rescue ship or a dramatic spacewalk. They just ride the invisible rails of orbital mechanics, trusting that the laws of motion will do what no rescue team ever could. At liftoff, the Space Launch System unleashes 8.8 million pounds of thrust, more raw force than any rocket since Saturn V, and about 17% more than Apollo's moon booster. That kind of power is not just about muscle, it is a threat in its own right. The SLS does not just shake the ground, it hammers it with an acoustic blast that peaks near 140 decibels, enough to shatter concrete and fry delicate electronics before the rocket even clears the tower. To keep the vehicle and the astronauts safe, NASA's engineers had to reinvent the launch pad itself. They built a water deluge system that floods Pad 39B with nearly 2 million gallons in under 2 minutes, creating a wall of steam that absorbs shock waves and reduces the reflected acoustic load by almost a third. Even so, every bolt and circuit on Orion gets tested by forces that would rip apart almost anything built for Earth. The team behind the pad stands between the crew and destruction by sound alone. Next comes the challenge of surviving what space itself throws at them. Inside Orion, the real line of defense against deep space radiation is not a bunker or a slab of lead, it's water. Nearly a metric ton of it, packed into tanks that wrap around the crew cabin and tucked behind the seats, forms a hydrogen-rich barrier between the astronauts and the relentless particle storm outside. Every drop pulls double duty, keeping the crew hydrated and acting as a shield that can more than halve their radiation dose during the Van Allen belt crossing. Waste is not just stashed away either. Used consumables and compacted trash are stacked strategically, plugging gaps in the shield and boosting its stopping power. To tackle the trickiest threat, secondary neutrons kicked up by high-energy electrons, engineers added borated polyethylene panels, thin but potent, around the seat backs. That tweak alone slices neutron exposure by another 15%, all without blowing the mass budget. It's a protection strategy born from necessity, squeezing every gram for survival. Manual control is not just a backup on Artemis 2, it is a trial by fire. After Orion separates from the upper stage, the crew has to guide a 25-ton spacecraft past a spent rocket body at a relative speed of 17,000 miles per hour. The margin for error is just half a meter laterally and 0.2 of a degree in orientation. That is like parallel parking a house while blindfolded and while both you and the driveway are moving. Every thruster pulse matters. If the capsule drifts outside that narrow window, the abort button gets hit and the entire maneuver is scrubbed. Crew hands on the sticks, eyes glued to the numbers. This is where human skill has to outmatch the chaos of deep space. There is no autopilot safety net, only precision, nerves, and a cockpit full of alarms. On board Artemis 2, the optical communications demonstration isn't just a science payload, it's the first taste of what deep space data could look like for the moon and beyond. At its peak, the laser link pushed 1 gigabit per second, enough to stream crisp 4K video across 250,000 miles, beaming back the lunar far side in real time. But the system didn't just work out of the box. Midway through the mission, a jitter in the fine-pointing mirror started scrambling the signal, slashing the margin to a razor-thin 3 decibels. Controllers on the ground and in orbit jumped on it, triggering a closed-loop correction that locked the beam steady again within 12 seconds. Later, a temperature swing nudged the amplifier's gain out of spec, threatening packet loss. A software patch from Mission Control recalibrated the bias, and the downlink snapped back, ending with 98% of packets received, almost no frame drops. Every glitch became a test of resilience, not just for hardware, but for the teams running the show. This isn't just a communications upgrade, it's the backbone for future lunar infrastructure, where missing a data packet could be the difference between routine and crisis. Orion hits Earth's atmosphere at nearly 25,000 miles per hour, fast enough to cross the United States in under 7 minutes. At this speed, the air itself turns violent, squeezing and heating into a sheath of plasma that can reach 5,000 degrees Celsius. But instead of barreling straight in, Orion's path slices down at a flight path angle of minus 12.5 degrees, skimming the edge of the atmosphere before bouncing back out to around 80 kilometers altitude. This is not a gentle glide. It is a calculated skip, like a stone thrown across a pond, designed to bleed off just enough energy to keep the capsule intact. Every detail, the entry speed, the angle, the precise geometry, decides whether the crew faces a controlled descent or an unsurvivable firestorm. Survival hinges on a margin so thin, it is measured in fractions of a degree. Orion's flight path angle at re-entry must stay within a razor-thin plus or minus 1 degree band. Veer outside that, and the capsule could either burn up or skip off the atmosphere into the void. The guidance system watches for even a 0.3 degree drift, firing microbursts from the reaction control thrusters to snap the capsule back on course. Each pulse is just enough to correct for slosh or shifting mass inside, but the room for error is almost non-existent. The crew rides out forces peaking at 6G, while the Avicoat X heat shield faces temperatures that push it right up to its design limits. There is no room for overcorrection, no time for hesitation. Every adjustment is a fight to keep the capsule inside that invisible corridor, because beyond it, there is no coming back. Right now, 4 astronauts trust their lives to math, metal, and the unknown. Every risk is real, because deep space does not negotiate. This is survival engineering at its purest. What would you bet your life on?